Welcome to qnawire.
Once again, this is a classic chance to see the law of conservation of energy in action. So we have a spring on the ground. I'm just going to draw it like that. And then there's a brick that's placed on top of the spring. This is the ground level. And so the spring is going to be compressed um, up to a certain height. The brick is still on the spring. So this is the specific distance in which the spring is compressed. We're going to call it X. And the purpose of this problem is to determine by how much the spring is compressed such that it's going to be able to travel a height h to the top of the wall. So there's a bricklayer that's building a wall, and so assuming this is the wall, and h being 3.6 meters above this initial position. This is the initial position right here. I mean, you can call it x naught, that's fine. And then the final position, you can call that x1. The total height is h. The mass of the brick happens to be 1.8 kilograms or 1.80 kilograms, two decimal places. The spring constant is 450 newtons. When the spring is compressed at the bottom right here, it has what we call elastic potential energy, which we can call US. So this is elastic potential energy. And then when the spring is released, it's going to lift up the brick all the way up until this height. At the maximum height, the brick has traveled h, and it has gravitational potential energy, which is mgh. Remember, elastic potential energy from the spring is 1/2 kx squared. Gravitational mgh happens to be the gravitational potential energy. Gravitational potential energy. And so we're applying the law of conservation of energy, where all the elastic potential energy is transformed to gravitational potential energy, UG. Just call that UG. So the goal of this problem is to find X. MGH, or rather 1/2 X, 1/2 KX squared, 1/2 KX squared happens to be equal to MGH because we don't have any losses of energy. Another thing that we're getting from the problem is that the brick loses contact with the spring, and so it's gonna, when it loses contact, it's gonna go to its uncompressed length. Okay, it's gonna go back to its original length, like that. Gonna solve for x, so 1/2 k over 1/2 k. These two cancel out, so x squared happens to be equal to this 1/2. When it comes up, it becomes 2, so 2 mgh all over k. And that helps us to solve for x by saying this is radical 2 mgh over k. Next step is we're going to plug in the specific numbers to find the value of x. So this is 2 times the mass, which is 1.8 kilogram. That's the mass of the brick. Times the g, which is acceleration due to gravity, 9.8 meters per second squared, times, so these are all multiplications, times the displacement upwards, which is 3.6 meters, and that gives us 0.53 meters. The direction that you take For the displacement, you could decide to say upwards. In this case, we're assuming that upwards is positive. In certain instances, you can say upwards is negative, just depends on the problem. Um, but in this case, we've decided to assume that upwards is positive. So once again, we have a spring that's pushing a brick upwards, a displacement of height h. The key to this problem is that there is conservation of energy from mu s or us, which stands for the elastic potential energy, all transformed to ug, which is gravitational potential energy. We plug in the formulas for elastic potential and gravitational potential and solve for x. X is radical of this expression, and then we end up with 0.53. Hope you enjoyed the video. Uh, Feel free to send any questions or comments, and have a wonderful day. Okay, bye.